Standard math concludes with a single numerical answer. In discrete mathematics, the goal is to establish that a property holds true for every possible case. This shift in thinking forms the core of your first 3 chapters: mathematical logic, set theory, and relations. Moving from familiar, real-world scenarios to dense pages of symbols requires a serious adjustment. The numerical intuition you relied on in algebra will not help you here. To get through these early assignments, you need a systematic method. We are going to walk through a structured framework for constructing formal proofs from scratch. Building these arguments requires abandoning gut feeling and relying entirely on strict, unbreakable logical rules. Step 1 of formal logic is translation. We have to take standard declarative sentences and strip them down into simple variables. Look at example 3 here. We take the statement, "Roses are red," and assign it to the variable p. "Violets are blue" becomes q. Connecting them with an or gives us the symbolic notation p or q. If we want to state the opposite, that roses are not red, we apply a negation, written as a tilde before the variable, like this, not p. Here is table 1.7. To verify if a combined statement is reliable, we test it by mapping every possible scenario in a truth table. We start by filling out the input columns for our variables, systematically writing out every combination of true and false. Finally, we resolve the output column row by row. If every single result in this final column evaluates to true, the statement is classified as a tautology, meaning it is always logically sound. Because they test every possibility, truth tables act as the binary foundation of logic. They give you a brute force tool to verify any mathematical claim. As your equations grow, drawing a massive truth table for every problem becomes impossible. You need a way to construct structured, line-by-line arguments. Let's examine this text in example 3. We have a set of premises about a daily commute. If I drive to work, then I will arrive tired, followed by the statement, "I am not tired." We extract the variables just like before. Let P represent driving to work, and let Q represent arriving tired. Next, we stack the symbolic forms of these premises. We have P implies Q, and below it our second premise, not Q. Drawing a line underneath, we deduce the conclusion, not P, or I do not drive to work. Notice the text explicitly states the rule used to get there. Every step must be justified by citing an established rule of inference, in this case, modus tollens. A formal proof centers on citing the specific, unshakable rule that justifies every single step in the progression. Now we take these rules of logical inference and apply them directly to number theory, using a method called a direct proof. Take a look at the theorem in example 1. If x is an even integer, then x squared is an even integer. To prove this directly, we start by assuming the initial hypothesis is true, then we define it algebraically. We state that x equals 2m, where m is some integer. Then we perform the core math. We square both sides of our equation. Squaring 2m yields 4m squared. Here is the crucial manipulation. To definitively prove our result is even, we need to show it is a multiple of 2. We factor out a 2 from 4m squared, leaving us with 2 times 2m squared. That leading 2 is our proof. We transformed a specific number into a generalized algebraic format. That is the essence of a direct proof, using strict definitions to definitively prove a property holds true for all numbers. Once you learn this framework, you can apply it anywhere. The exact same logical steps map directly onto your work in Chapter 2, Set Theory. Here we see the commutative law for sets, which states that the intersection of A and B is equal to the intersection of B and A. Let's prove it. In set theory, to prove 2 sets are exactly equal, there is a specific rule. You must prove that each set is a subset of the other. We begin by taking an arbitrary filament x from the first set. We then translate the intersection symbol into a standard logic operator, writing that x is in A and x is in B. Now we use the standard commutative law from Chapter 1 to flip the order around. Once the variables are flipped, we convert the word "and" back into an intersection symbol to complete the subset proof. The mathematical symbols and shapes change from chapter to chapter, but the underlying engine of formal proof remains exactly the same. We started by translating simple English sentences into simple variables and scaled that exact same logic up to rigorously prove relationships in set theory. Success in this course requires a strict layout. State your hypothesis, manipulate it using algebraic or logical rules, and cite the justification for your conclusion. Look at the problem set in exercise 1.4. Grab a pen, pick one of these early questions, and apply this exact step-by-step structure to solve it. Mastery in discrete math depends on internalizing the logical framework that allows you to prove any mathematical truth from first principles.